Thank you. So yes, my talk is about bending simulation framework for rapid feasibility checks of sheet metal parts. We start with a CAD geometry. We start with a CAD part with no feature information, no design parameters. And normally when you have a part like this in a CAD system, what you can do if a CAD system contains a sheet metal workbench, you can feature recognize the part. You can extract such properties as material thickness. You can also extract cutting contours, bendings, cutouts, and then you end up having the flat pattern that you can use as a production drawing and pass it to fabrication. One question that remains unanswered, though, is whether the part is actually feasible or not. And this is the main question of my talk. How do we check if a part is infeasible? Here on this image, the part is not actually infeasible, but it's still tricky to fabricate on a shop floor because it would lead to collisions with punch tools if you do straight punching. So by infeasible, what we mean is infeasibility with straight punching, because in production, in shop floor, there are some tips and tricks that allow you to do some tricky shapes like here, and such precision tooling is out of scope of my talk. To put this talk in a context, we are mostly interested in manufacturing as a service platforms. This is a growing industry, also sometimes called like digital manufacturing platform or on-demand manufacturing platform. And the use case behind those names is as follows. A customer communicates the design as either step file or proprietary format to specialized CAD service. It's not necessarily a manufacturer, it can be some hub. And as a feedback, the customer receives a manufacturability report and also the estimation for fabrication costs. So in order for these two feedbacks be possible, in order to receive this manufacturability report and quotation, what is necessary to do at the end of the manufacturer or at the end of this specialized CAD service, it's necessary to analyze the part and to feature recognize the part, if we are talking about traditional computational geometry-based methods. So we've been facing this use case of manufacturing as a service platform quite often, and we came up with the notion of MaaS kernel. For the lack of a better name, MaaS is manufacturing as a service. So we tried to componentize all useful functions under the umbrella of one, so to say, algorithmic core. And what it contains is data exchange tools, like to read a step file and also to export also step file, but not only, you can also export a DXF drawing and GLTF for web-based visualization, SVG files for preview, PNG images and whatnot. Then such a MaaS kernel should necessarily have shape interrogation and feature recognition tools, because you normally want to analyze your shape before you come to conclusion at the machining time and manufacturability issues, if there are any. For assemblies, we need to also be able to work with assemblies, break them down onto individual parts and extract bills of materials. We need specific tools for manufacturability checks. For sheet metal parts, we need to be able to perform two-dimensional irregular shape nesting. For delivery, we also need to solve the 3D nesting problem for packaging. So all these common functions, they have a specific purpose, and they can become componentized into specific software components. In 2017, we published an open-sourced framework for feature recognition. This framework we named Analysis Situs, and it contains basic data structures and algorithms for feature recognition. And we also started to create plugins on top of this open source kernel. One of such is sheet metal unfolding, sheet metal recognition and unfolding, and my talk belongs to this sheet metal recognition and unfolding scope. The main apparatus that we are using is attributed adjacency graph. We turn the boundary representation of a model of a CAD solid into a graph. In this graph, each node represents a CAD face, and a link in a graph represents the neighborhood relationship between faces. We also have an attribute, like in the classic approach, you need to encode the type of a dihedral angle between CAD faces. Here, this attribute is color-coded, green for convex, red for concave. And with the help of this graph, it's very easy to iterate CAD faces one after another in the order how they are connected to each other. I also have to note here that we are using OpenCascade, which is open source geometric modeling kernel. And in OpenCascade, it's not that easy to iterate faces in their adjacency order. So that's another point in having this formalism on top of the BREP. So our idea when we recognize a sheet metal part is to be able to split the part into two sides. We want to extract the inner shell of a part and the outer shell separately. And if you map this to the graph model, then you will see that basically in the graph you have two connected components. So there are two clusters of nodes in the graph, and they are not connected to each other. If we are able to split a part like this, then the part is said to be two-sided. And this is one of the strong heuristics which we use in our feature recognition algorithm. Another strong heuristic relates to thickness faces. Thickness faces are the faces that separate those two sides of a sheet metal. And if we keep them alone in the graph, then we will see that in the graph we have a closed loop of nodes where each node contains exactly two incident edges. So the degree of each vertex in such a reduced graph is equal to 2, and this is the second key heuristic that we use in our feature recognition toolbox for sheet metals. So the goal of feature recognition is to take the dump model without any information about features and give it some semantics. The features that we recognize are the sheet faces, thickness faces, bands, including their properties, like angle, radius, axis, and cutouts, holes, and some other features like engravings, notches, and whatnot. So that is basically to recognize every single face in a CAD solid, not leaving any face unrecognized. So the feature recognition process should be complete. We start with a face that we call a seed face. It's normally the one having the max area in the model, but there are different rules how you can also select the seed face. Then we cast a ray inwards the material, and this way we find the mate face, the face on the opposite side of the sheet metal. Once we have these two faces, we propagate over the faces using AAG, using the graph, and we propagate over the smooth dihedral angles. So this process would terminate at the boundary of the part where the dihedral edge becomes sharp. And this way we accumulate those shells, and here we can already check that we have exactly two connected components in the graph. All the faces that remained uniterated we declare as thickness faces, and for them we check their own subgraph. Basically here we check that if we have a loop, then it should be closed, and and the degree of each node is necessarily 2. Sometimes we have just one isolated hole, which is a degenerated case where we have just one floating node of the graph. This is also okay. Another result of feature recognition is unfolding graph or unfolding tree. This is a derived data structure that holds parent-child relationships between flanges. The nodes in this unfolding tree correspond to flanges. They store the information about a local transformation of a child flange with respect to the parent flange, so that we have enough information to flatten out the part into the drawing, into the flat pattern. Also, in the links of this graph, we still keep information about bands, because this information will be used later on in the simulation. So far, we haven't touched the simulation part of this whole story. One very important aspect of recognition is how we group bands together. So one early mistake that we made is we grouped bands simply by their geometric properties. Like here, band 9 and band 10, they have all properties identical. They have identical axis, direction, up and down, inner radius, angle. So we decided to group them together, but it's actually incorrect, because when you start to simulate the unfolding process, you will see that basically those bands easily become ungrouped, and they are not aligned after you unfold the part here over the band line number 2. So we needed to solve this problem, and the approach that we are currently using is we use the information about cutouts that you have to recognize first in order to constrain the bands together. So here in the A picture, we have 6 band features. Out of these 6 band features, we can obtain 3 band lines, 3 band features composite, because those band features, they cannot move freely. They are constrained by the presence of this cutout here. And this information is something that we introduced in the feature recognizer to facilitate later on the simulation logic. But if the cutout is broken like this, then you do not necessarily constrain those bands like number 2 and 3, 4 and 5, because you still can constrain them, but it's not required, and you can leave this degree of freedom to the simulator. So once the part is feature recognized, we need to finally analyze if the part is infeasible. And in a sheet metal part, having n band features, there are like n factorial permutations of this bending sequence. So the search space is vast, and probably the worst idea is to try to iterate all these band sequences, trying to find some feasible one to prove that the part is feasible. But we actually started with this bad idea. We started to iterate not all possibilities, but we limited the number of iterations with 100 or something, and we just tried to find any feasible configuration. And if we were not able to find any, then we concluded that the part is at least problematic to be fabricated. So something is complicated about such a part. Geometrically speaking, we took the flat pattern, we took all the band lines, we projected the band lines onto the flat pattern to obtain a foil shape, like a thin shell that we started then to fold back. So we folded each flange one after another, and this way we obtained a graph of intermediate folded states of the geometry. And once we hit a collision, then we come back to the previous state, and we start again with a different flange. So effectively, if we formalize this process, when we have a graph with the source node with the blank sheet, and we have a destination node with the folded part, and we try to find a way through this graph, through all the intermediate folded states of geometry until we reach the finished part. And sometimes it happens that there is no such path because, for example, it's the last layer. Here, all combinations will lead to collision with the punch. And it means basically that computationally you have to iterate all these paths, and this is not suitable, especially for our use case with manufacturing as a service, where users typically want to have instant feedback. Like you upload a CAD file and in few seconds you already know the price of fabrication, you have your drawing, you have your manufacturability feedback if any, and you know the part is feasible. So the solution to that we came up with is reverse search. We start rather from the folded state of geometry, and in the folded state of geometry we try to find at each iteration the set of bands that can be regarded as final. Once we found those final bands, we unfold them locally and we continue. So this process will end either when the part is completely flattened out, so this would mean that the part is feasible, or it will stop at some point where we could not find any final bands. This would mean that the part is infeasible. Here in this approach, we do not try to find a sequence. We try rather to prove that there is no sequence at all. One question though is at each stage in this algorithm we have to move flanges around. So we have to do this local folding and unfolding. And basically the BREP structure that we have in the beginning after we imported the step file is not that flexible. So you cannot easily modify it. One way how you can make it more flexible, one way how you can facilitate this folding and unfolding mechanics is you defeature the band that you are looking at right now. You rotate the rest of the part, the flanges that you want to fold or unfold, and you build another solid of revolution for another band angle. But this modeling technique, although it might give you very precise modeling results at each intermediate state of geometry, it's pretty computationally heavy because at each iteration we try to go for accuracy, so we model for precision. That's not exactly necessary if you want just to simulate collisions. So our take here is different. We use the information about the recognized sheet sides because we already know the inner shell and outer shell of a sheet metal, and we can take just a sparse triangulation out of the analytical surfaces, and we can use this triangulation for collision tests. And here we actually ignore the presence of thickness faces. We just eliminate them from the simulation model. And we also eliminate from the simulation model the curved bands, because this is where you normally have high concentration of triangles, and we would want to go for very sparse simulation, because what we are going to do is we are going to rotate flanges, and at each iteration we will check for collisions. So too heavy triangulation is an obstacle. The way how it would work is once we have the simulation model without band faces and without thickness faces, composed only of meshes, we can use any grouped band as a splitter. So we come back to the unfolding graph that we obtained as a result of feature recognition, and we split the graph onto two halves, red and green in this case. Red means left, green means right. And basically the idea is just to be able to split the part like this, so that one side of the part goes one way around the bend axis and another part goes other way around the bend axis. Then we can add here at each frame of the simulation the collision boxes that we will be using to check if the flanges collide with other flanges in the part. So basically each flange here is a pair of faces, a pair of meshes, mesh objects, and we can use them as individual bodies for collision. At each iteration, we can build this bounding volume hierarchy and use it to perform collision checks. So one collision check that we are interested in is the collision of the part with itself. We can also employ the same mechanism of collision boxes and bounding volume hierarchies to check for collisions with the tools. In our algorithm, we mostly use punches of different shapes. We use gooseneck punches, we use straight punches. You can also add here dies or some other machine components, if you will, like punch holder, for example. But having punches is basically already good to know, to assess the manufacturability of a sheet metal part. It's also very important to have these band groups recognized properly, because the flanges will go around those band axes, and band axes, they are coming from the groups. If we did not group those bands around the cutout here, then the part would just fall apart, it will break down on the very first simulation frame. So band grouping is really important. A few examples in the end of my talk, how it works. For this part, for example, this part, I mean, it doesn't look suspicious whatsoever. If you load it into feature recognition software, you will normally end up having all the features recognized, and you will have your flat pattern. The thing is that it's not easy to access the bands inside the model, and this is what the simulator would report. Like, the simulator would be able to unfold 3 flanges, the smaller ones, and then it will stuck here at this band line because no tool, and it will iterate over all the tools from the database that will load it. No tool will fit into this band, so the part will be flagged for a human review. Again, collision doesn't mean that the part is completely infeasible, but it would mean that there is a certain hidden manufacturing effort, and this has to be communicated to the human engineer. The same situation happens here. With this part, we have smaller flanges that are easily unfolded, but after that, you cannot easily access any of 4 bands that remain in the folded state of geometry. A little bit different case here. The part is almost okay, but we do not have reliefs near those inner flanges. And when simulator starts to unfold the part, it hits self-collision condition, because there is no little proximity, and this is regarded as a design issue, although probably not super important, but still it's something to be communicated back to the engineer. Here it's a simple example of a narrow flange. There is just no tool in the database that would fit into this narrow flange, and with specific tooling it might be still possible, but because those DFM checks, they normally relevant to one or another shop floor with specific tooling, then it's useful to report cases like this as well. And here in this case, flanges just happen to be coincident to each other without any proximity gap, and again the part will be reported as part having self-collision simply because there is like coincidence between the meshes in the simulation model. Normally, in a good design, you would leave a little bit of proximity between flanges. A few limitations remain to work on. One very obvious limitation of the algorithm is its inability to work with flat hams. Flat ham is a completely closed band. No tool can be accommodated in the generated inner radius. So such parts, such hams, they require specific processing. Then the rotation mechanics that I presented when we select a bend line and we start to rotate halves of the model around this bend axis, it's actually an oversimplification, because normally when you unfold the part, even locally, you have to take into account the material properties, and you have to come up with the bend allowance distance and respect the key factor. This doesn't happen yet. So the transformation that we need to take in order to unfold the part is more complicated than rotation. And then performance-wise, if we are working with perforated sheets that are not uncommon at all, the even sparse meshes that we obtain from the CAD kernel, they happen to be too dense. So normally what we can do, and we should do, we should defeature smaller holes and cutouts before simulation, and this way to simplify the simulation model. This is not very complicated to do, because we have the BREP model, and we can just cut off the corresponding features from the topology graph of the model. That's it. Thank you for your attention. I'm happy to answer any of your questions.
Thank you, Sergey, and excellent presentation and many details. Is there any question?
Thank you, Sergey. Very good presentation.
Thank you.
I just have a detailed question about the page 9 of your presentation. Like as you showed in a graphic, like
yes,
you showed a graphic for the representation of a model. But I'm just curious, like my question is like for a certain model, is a graphic representation unique, or it might have different types or different formats of the graphics for presenting representing a model?
you can imagine a model like a box shape, for example. And if you give it a different shape, if you extrude it a little more or less, if you substitute faces with curved geometries, this graph will still be the same. So the graph itself doesn't capture the shape of the model. It to some extent captures the topology of the part. So for a boxy shape, you will have here like these 6 nodes and 12 edges, and you'll have this information about the dihedral angles, but that's not unique descriptor of the shape. So it's like a supplementary data structure that we use, but we still have boundary representation to work with, and there is a link, like both data structures, they live in memory. We have in memory both the boundary representation and the AAG, and there is a link from AAG to the boundary representation to query geometric properties. Does that answer your question?
So, yeah, so that is like in summary, like the topology of the graphics will be the same if you try to, okay, I see. I just have a follow-up question for the maybe page 20 to 23.
20 and
yes, like actually like this yeah, you talk about the bend grouping.
yes.
My question is like is a bend grouping like related to where you start? And as I think in the page 23 you said like there is a bending sequence. So
Yes.
I'm wondering, when you do the bending, are there any technique or any tips of where to start and where to end?
Well,
or it's just a line?
Yes. So how it works for us, this bend grouping happens before simulation and before trying to find any sequences. So this is still a part of feature recognition. So there is feature recognition, and then on top of it we have simulation. Bend grouping is still a part of feature recognition, while here, well, actually, I cannot say that we went very in-depth with this approach. We started with just natural sequence, like 1, 2, 3, 4, 5. And then we after a few experimentations, we just gave up with this approach because it appeared that while this approach is a must-have to find an optimal bending sequence, we were not interested in finding an optimal bending sequence. So basically, we just needed to know what a sequence doesn't exist. And I think that this question of where to start is something to address when you really want to derive the optimal sequence, right? While we always start with the folded part, and then we just try to unfold, each band subsequently, and if you see that there is like band number 1 and band number 2 that can be unfolded, then we unfold them, and we restart this process from the temporarily and partially unfolded state of geometry.
Thank you so much.
You're welcome. Thank you.
Okay, thank you, Tian. Is there any question? Other question? Or is there any question from the online audience? If you have a question, you can use your microphone, ask directly. Okay, well, so if we don't have more question, should we have a break or we keep on to the next one? Okay, so we keep on.
Okay, thanks.
Thank you.